At this point in the lectures, we've talked about infinite series and the kinds of tools that we need to figure out whether or not we're even allowed to add up infinitely many things. So we have lots of convergence tests to figure out whether or not an infinite summation actually gives us a real number at the end of our calculation. And from there, we started to talk about power series. If I can calculate an infinite sum, maybe the formula that I have depends on some variable x. And for different values of x, I'll have a different sum. I'll have a different output. That's exactly what I need to define a function. And most recently, we've talked about how it is that power series play nicely with derivatives. Let us investigate a little bit further and try to explore some of the structure that power series give us. So far, a power series is just a whole bunch of powers of x. We're adding them all up, and each of those powers has some coefficient attached to it. So we are adding up infinitely many things, and we're concerned about making sure that that infinite sum will converge. But the coefficients themselves are kind of a mystery, right? They're just some numbers. What could be special about them? What could be important about them? Let's think about a power series. And here we've got a very abstract looking series here. We have centered this series at the value a, and we have some coefficients. The first of these coefficients is C0, the second of these coefficients is C1, the third of these coefficients is C2, and the subscripts here are indicating which power of x minus a that coefficient is multiplied against. Now, what can I say about these coefficients? Well, I don't exactly know what number a is, but a is always going to be in my interval of convergence for this power series. There's only 3 ways a power series can converge. The power series is valid for all x on the real number line. Maybe the power series is only valid for x in a certain interval, and the number a will be dead center in that interval. Or the power series only converges for x equals a. No matter what, I should be able to put x equals a into this formula, and what would I get? I'd get my C0, and then I'd get a 0, and I'd add on a 0, and I'd add on a 0, and I'd add on a 0, and so forth. Ah, well, I know how to calculate that sum. That's just going to be C0. So the value of this function at x equals a is the first coefficient, C0, the constant term if this was a polynomial. Well, I know that when I take my derivative, the constant term is going to go away because I'm using the power rule on every single power of x minus a. Okay, well, what is the derivative of this power series? The derivative of this power series starts at C1. That's the same coefficient from my previous slide. Then I've got twice C2 times x minus a, 3 times C3 at x minus a squared, 4 times C4 times x minus a cubed, and so on. Again, this is just the power rule that I was using in my previous lecture. And let's try plugging in x equals a again. Then The derivative of my power series, evaluated at x equals a, is my second coefficient from the original power series. And I can keep going. Let's see what happens next.